Okay, is that on? Is this on? Is this on? Yeah. Yes. But do I need to keep it this close, or is it okay if? Oh, okay. So it is picking up when I'm. Okay, great. All right. So I wanted to start by showing something on Macaulay too, and then I'll start using the board. But so I have defined some ideals in Macaulay too, which are all ideals in polynomial rings. So if you should think about those as these ideals that I'm writing as sort of I3 will be ideals containing all monomials xi square xj, where I and j are from 1 to 3, and I and j can be the same. And similarly, I4 is where I now have x1 x4 square, so I have fourth variable. I5 has the extra variable with x5, so the same. And maybe I should do transpose. Let me show off my Macaulay's 2 skills. I6. So that has like many generators, but they're all xi square xj, where I and j can be from 1 to 6. So what here is maybe a question. So I'm going to now compute its free resolution, which if you don't know much about, just for us, all we care about is some table that Macaulay 2 will spit out. So here is so Betty res I3 will give me the free resolution of I3 as a module over the 3 variable polynomial ring. I'm sorry. So that you can. I don't. Okay, so then I4 is here. And I'm hoping that someone can notice the pattern. So I'm scrolling, sorry. And I5. So can anybody notice the pattern here? Like what's happening as I'm increasing the number of variables? Can you notice some relationship between the different Betty tables? And you shouldn't worry about what the numbers are. It's really all we care about is whether they're 0 or not. I6, I'm sorry. Oh, it's not supposed to stabilize in the trivial sense. So let me just do it all over again. I6. Okay, so what is the stability property that somebody's? Yeah, it goes down the diagonal, but there's also the row in line 2, right? Yeah, so that's kind of the main thing that I wanted to talk about. So note that these ideals that I have are I3, I4, I5, I6 are related because you just take x1 square, x2, and x1 cube, and then take the symmetric orbit of that, symmetric group orbit of that. And I want to talk about some results related to this and how you can explain what you're observing here as well. So I think I'll quit this now because I have my notes here. Okay. So here's a result that kind of proved by Murray, which let me first state that. So theorem of Murray, and it's a very beautiful result because it's kind of unexpected, I think, and I don't really know why anybody would have expected this. So his statement is the following. So you take a chain of ideals. Go on. And whenever I write a subscript that is supposed to indicate an ideal in the n variable, so I3 is in the 3 variable polynomial ring, n will be in the n variable polynomial ring, and so on. And they satisfy the property that each in is monomial, so generated by monomial elements, and stable under the action of Sn, which acts on the n variable polynomial ring. Then Murray proved a result that we kind of just saw. What he proved is something about the free resolutions of each of them. He proved that the free resolutions stabilize in the following sense. So there exists a capital N such that, and I think drawing a picture here is better. What he proved is that so beta of I capital N, sorry, I capital N, it will look like this, where there is some junk in the beginning which you can't really control. And then there are some kind of like lines shooting off this. So this will, let's say this is sort of, this kind of like stops here. And then from here, you can get the free, you at least know where the non-zero entries of beta in plus 1 is. It is going to be again the same junk as before in the beginning, but the numbers could change, but the non-zero and where it is 0 and non-zero can be determined there. And then you have the same lines as before. And if the black dot was from the previous one, there would be another extra like thing here. Does that make sense? So all yes. Yeah, there could be. Yeah. There is some, yes, that's right. The number of lines can be anything. Like it can be arbitrarily large, but finitely many for each in, and it goes on. Like so, when you want to go to in plus 2, you add, like, let me just like add. Oh, diamond is for in plus 2. I don't know why I'm using. Okay, I use colors. I'm not colorblind, but I. Okay. Shit. But hopefully you get the idea of what the results. And again, I personally don't know why you would get this result. I mean, the way that Murray proves this is using sort of combinatorial methods. So if you have a monomial ideal, you can attach to it a simplicial complex whose Betti numbers in the usual sense, the simplicial homology captures the TOR of the corresponding monomial ideal. And he proves some kind of stability results for those simplicial complexes. So for me, like that's not, I mean, it's a combinatorial result, but there should be some kind of underlying algebra that you're seeing through this, and that's kind of what I want to study. Are the new entry? Yes, that's right. So just to kind of, again, I thought I could use colors to describe it, but I think I made it harder to understand. But yes, that's what I mean. So all I'm saying is that the newer entries in in plus 2 will be these three. The new entry in in plus 4 will be this, and another one, the next one is the same lines. Because yes, go ahead. Yeah.
In the picture earlier, you had this one row, this one line,
you just keep adding. So in that case, there, Murray's result is then saying that there are 2 lines in the Betti table, and then that starts showing at I3 or I4 maybe. And then to get I5, you just added an extra entry along those 2 lines, and you keep on going. Does that help? Yeah. Okay. Yes. This lines can have, that's a good question, and the lines will not always have slope 0. As we saw, it doesn't have slope 0. Slope 0 would just mean like rows, right?
Yeah,
Or 1. Yeah. No, it can have so for example, if you take this, so if you take this example where Jn is generated by x1 to the m all the way until xn to the m. If you take the mth power of the ideal, this is a regular sequence. We know what its free resolution looks like, and this will have slope m minus 1. So this is one example of that, and yeah, so in general, no. So maybe okay. So this is what I'm trying to do. Problem.
Sorry.
Yeah.
Is the color coding of the diamonds to sort of indicate that top one would then depend on this?
No, it is the color coding is irrelevant. That is why it is yes. Thanks, and it is completely irrelevant. In fact, it is. I think it is only going to depend on this line, and yeah, and hopefully that will be clear. So problem is sort of interpret Murray's result algebraically. And yeah, this is kind of vague, and I don't. Yeah, I don't have a priori, I don't have a specific like question, but I want, like, for example, one thing would be given an ideal I, what contributes the lines of a fixed slope? For example, can you give me another module that is related to I, which sees everything of slope 0, slope 1, slope 2, and so on? Okay. So yeah, so this result is not coming out of nowhere. It is part of this uh, this kind of program of studying symmetric ideals in polynomial rings, where the number of variables increases. So rather than thinking about a symmetric ideal in one polynomial ring, somehow the point is that if you consider chains of symmetric ideals in increasing number of variables, they become nicer asymptotically. And all of that can be traced back to this one result from the 60s. So this is another result of Cohen from, say, 67. And it's a finite generation result, essentially. So in this setting, so let I1, I2, be a chain of let me say homogeneous, just for the sake of it, and everything I do will be for homogeneous stuff. So homogeneous symmetric ideal. So I'm dropping the condition that it is monomial. In this case, I just want it to be homogeneous and symmetric. And as before, with In is always going to be in the n variable polynomial ring. Then there exists F1, F2, Fr in some I capital N, such that In plus T is just generated by the S n plus T orbit of the Fi. One for all T greater than or equal to 0. So what I'm saying is that you give me a chain of ideals for there is a n large enough such, and so I can go far away in the sequence and find finitely many elements in one of those ideals, such that every successive ideal can be just prescribed by taking those finitely many elements and then using the obvious Sn plus T action that will be there in the larger and larger polynomial ring. This is characteristic phi and works as long as the coefficient ring is Noetherian. That would have been like x1. So that would start stabilizing from n equals 2. And the generators you need is x1 cube, which you see even in n equals 1. But in the second variable, you get x1 square, x2. And this also works if you drop the homogeneous condition, by the way. And maybe perhaps the better way to say this result is kind of by passing to a limit, which is kind of what we will do soon, where everything becomes cleaner if you pass to the limit. And what this is saying is that if you go to the limit, I mean, and whatever, then you're saying that every symmetric ideal in the infinite variable polynomial ring is finitely generated up to the action of the infinite symmetric group on it. Okay. And there are many other results that have since followed. So let me say a few more results along these lines. So people have also studied the Hilbert series of these. So what you can do is, if you give me such a chain, you can form a 2-variable Hilbert series in variables, say, S and T, where T keeps track of the internal grading in every polynomial ring, and S keeps track of which polynomial ring you are in. So what I mean is that you can define, so given such a chain, define H, I'm gonna just write I, even though it's a chain, so Hi of S comma T. This is supposed to be the sum where the T variable is keeping track of just the Hilbert series of In, and S is keeping track of, I guess I just need N equals, say 1 to infinity. And S is keeping track of like which polynomial ring I'm in. Okay. And this, and in fact, this is a result of Nagel-Romer. This is a rational function in S and T. And this doesn't just follow from Noetherianity. You need more work. And there's some final results about what the denominator can be and so on. But I don't want to get into. Let me just, for the sake of it, say a few more things, which is that Nagpal Snowden have studied S infinity. So this is in S infinity stable ideals in the infinite variable polynomial ring. Up to, and in fact, they have a nice classification of these ideals up to copotency, by which you say that two ideals are copotent if I and J are copotent if I to the N is contained in J and J to the M is contained in I for some N comma M. And so, it's kind of up to radical, but radical is not very well, it's not good to talk about. It's better to talk about copotency in these infinite variable cases. And they have, and in fact, it's kind of complicated. They have the classification there requires a triple where the first thing is a partition of infinity of the natural numbers, essentially. The second thing that they need is a natural number, and the third thing they need is a subvariety of fine space of any an, and which somehow depends on the lambda and e. And so there's it's sufficiently rich. I mean, it's not a trivial class of things to study. So them as well as you are also studying S infinity equivariant modules over this. So there are quite a few people studying this. And from the point of view of free resolutions, Murai's result is motivated by a conjecture of 4 people. And all of this suggests that there should be some non-trivial finiteness in every such chain. And this is a conjecture of Ley, Nagel, Nguyen, Romer. The conjecture. So given such a chain, their conjecture is that one, the projective dimension and they conjecture that the projective dimension and the regularity are eventually linear. So let me say there exists A in N such that the projective dimension of In is equal to N minus A for N sufficiently large. So the projective dimension will be at most N by Hilbert's SSG theorem, and they are saying that it is equal to N, kind of finite kind of. It's linear, I mean, yeah. And the second conjecture is that there exists B comma C in N, such that what is called the Castle-Novo-Mumford regularity, which is again some kind of invariant, is equal to B N plus C for N sufficiently large. And these are both still conjectures, but hopefully it's clear that Murray's result proves this at least for symmetric monomial ideals. Is that more or less clear? Because kind of, I mean, you have some junk in the beginning, and then again draw my picture, this time without colors. So you have some junk, and then you have these lines kind of shooting off like this. And the regularity of IN is going to be this. And the regularity of IN, is going to be whatever. Well, let me just say this first. So from the Betti table, you can read the projective dimension and the regularity. The projective dimension is just the largest vertical column in which there's a non-zero entry. And regularity is the largest horizontal row in which there's a non-zero entry. And so the regularity will be like this, whatever this row is. And as I said, by his result, you can kind of, the next, the slope of this will give you B, and then the offset of that is like C, because for n+1, it's just adding entries here, here, and here. And similarly, projective dimension of is just, again, you're just adding one to it all the time, which is this. Is that clear? I'm sorry, I think I mumbled there. Okay. So yeah, so we know this for symmetric monomial ideals, but again, it is it's open more generally. Like if it is not a monomial ideal, it's not clear how to do this. And that's not, people know it for combinatorially defined ions. So if these are edge ideals and so on, it's known, but I think it's still kind of open, and we don't know how to do this in general. And I kind of want to explain one path forward, which I executed for a very small subclass, which I think is the right way forward. Okay. So let me erase. And the idea is fairly simple, which is that the projective dimension conjecture is really a conjecture about depth. And in that case, it is a stabilization result to the on the nose, because by what is called the Auslander-Buxbaum formula, this tells you. So there is a relationship between projective dimension of any module and what is called the depth of a module. This is always equal to the dimension of the ambient ring. Okay, and then their conjecture can be therefore restated as saying that the depth of ion is equal to A for n large enough. And yeah, as I said, so therefore what you are supposed to do is somehow again pass to some kind of limit and show that the limiting thing has some depth, and then you can somehow percolate it backwards. But the nice thing about depth is that there are many other and if you don't know what depth is, it's fine. Like you can just you can use this, but I will say exactly what we need about. The nice thing about depth, especially for the nice thing about depth is that there are many derived functor tools that you can use to kind of detect depth. Okay, and so this should suggest the following: that if you want to show that depth stabilizes, what you really want to maybe show is this. So using this here, the idea is endow. So for fixed I, endow this x of a comma in over the n variable polynomial ring. So in this case, S is bad. I can use R, I guess. Rn is supposed to be the n variable polynomial ring with some algebraic structure. And some algebraic structure with an n grading. And prove finite generation. results. So yeah, what I mean to say is that you can take one of the nice things about depth is that the smallest cohomological degree where x, I, k, comma, in is non-zero is precisely the depth. Okay, so if the depth of in is a for n sufficiently large, that should mean x, a, k, comma, in should be non-zero for large enough n, and that should be the first one that is non-zero. Whereas x a minus 1, x a minus 2, all the way until x 0 should vanish for all large enough n. So you want to somehow fix an I, take these things as n varies. So remember that all of these are modules over, in fact, they're just vector spaces. And you want to somehow give it a structure, an n-graded structure, and prove some kind of finite generation results as an n-graded object. So what would that mean? That would mean that, so say x0 is finitely generated. That means that if you think about the grading, now the grading is keeping track of which variable polynomial ring I'm working in. Because it's finitely generated, there'll be finitely many objects that are generated. So either it is always 0 eventually, or always non-zero eventually. By finite, if you have finite generation, you can't kind of like have interspersing non-zero things infinitely often. And so if it is non-zero infinitely, if it is finitely generated and actually non-zero for infinitely many n, it should be non-zero for all n, and therefore the depth would be 0, and the potential dimension would be n. But similarly, if let's say x0 is therefore vanishing, then you look at x1. If x1, the same thing happens. It's either going to be 0 for large n, or it is non-zero for all sufficiently large n, and you can play the same game. Okay, and of course and if you kind of play around with this, you will realize that you can't actually do this because if you like look at in to be generated by just due to grading reasons, not only is this like an n-graded object coming from this grading, in themselves have grading, so there's another internal grading. And what that means is that if you look at in to be the ideal chain with the maximal ideal, you might think that this is possible. But if in was generated by, say, the squares of the variables, it'll become more or less clear that this is not possible. And so the key point is that you should not do this, but you should instead do what is called the local cohomology. So let me just erase this and replace it with the local cohomology. So that change in color was accidental, but prescient. You do this, where these are called the local cohomology modules with respect to the maximal ideal in the n-variable polynomial ring. And the local cohomology modules are the same property of x that I just said. It also detects depth. So the smallest non-zero thing would be where it is. Yeah. Yeah, it is. The problem is that if you look at x, right? So x0 of k comma Sn mod the squares of the variables, it will be in degree like 2n minus. It'll be in the internal. It'll be in the polynomial ring degree like 2n minus 1 or something. So x0 itself you'll have to get maps from in the n-variable polynomial ring, you have an element in degree 2n minus 1, and then somehow you have to jump up degree and also the polynomial ring degree, and that can't happen if you are trying to do something kind of uniformly. You can give a grading. I mean, there is a grading, but you can't. Whatever structure you then define will not respect the grading, and that somehow cannot happen. I mean, maybe a better way to say it is if you define it for the x k comma k, that same definition would just say that for x k comma s mod x1 square, x2 square, x3 squares, all the maps will be 0. So you can't define it uniformly, is what I'm saying. Yeah, I mean, yeah, I can't. So the idea now is to endow this with some algebraic structure with an n-grading and prove finite generation results. But if you know anything about local cohomology, this is kind of a lost cause in the beginning because if you don't have any chain, you just look at the local cohomology of say an arbitrary ideal in a with respect to the maximal ideal, it's not even going to be finally generated as a module over the polynomial ring. Like just in, you don't vary anything. You just like have hi of mi, and that's going to be not finally generated. But somehow I think this is still the right way to go, and I will kind of explain why I think that is the right way. So somehow all the non-finite generation noise is in finitely many degrees. Yeah. This is not. This is a conjecture. Yeah. Yeah, but that is. Yeah.
Is there any way to approach from that?
No, because that is dependent on the Noetherianity of the Rees algebra. Whereas this is I mean, okay, so that is, and okay, yeah, if you are approaching it that way, then it would be about like taking a limit and then you're working in this infinite variable polynomial ring, which is kind of what we are going to do, and use some results there. But it is not, it will need more structural results, just the Noetherianity of the Artin Rees algebra. Okay. So any questions?
This was known for
Symmetric monomial.
some binomial ideals.
Yeah.
Is this known for like ideals of points?
You have to give me a chain. How are you giving me a chain?
Somehow maybe embedding points, like larger and larger dimensions, or just maybe
Adding a point.
completely adding a
I don't know the answer to that. Oh wait, if the depth is 0, sorry, those will have dimension 0. Yeah, in that case the projective dimension conjecture is trivial, because that is just saying that the projective dimension will be n eventually, which is true. The regularity conjecture, I don't know. In that case, yeah. But oh, then it's no. What do you mean constant regularity?
Sorry, that's the Hilbert function we did was
Are you? Yeah, I don't know. Yeah. Yeah, but the projective dimension one is somewhat simpler. Okay, let me just look at my notes and I will. Okay, so and what I did do is I have executed this idea for chains of GLN stable ideals. So if you further have the condition that these ideals are stable under the action of GLN, there is a way to do it. Of course, it's a much restricted class even compared to symmetric monomial ideals, because symmetric monomial ideals are those which are stable under the action of like monomial matrices, which are matrices which only have one non-zero entry in each row and column, which could be any number. But the nice thing is that whatever I've done also applies for certain families of modules. In fact, like which I will define. So it's a more algebraic result in that sense, and it also gets at what I was saying about extracting the slope stuff. Okay, so let me now introduce what I wanted to talk about. So definition. Okay, and maybe before okay. Let me just say a few things. So what I will have is I will work with K. It's always going to be an infinite field. And for me, I will work of characteristic P greater than 0. And I have, whenever I write V, this will be the infinite dimensional vector space K infinity, which you should think of as, having bases E1, E2, E3, En, and so on. And GL or GL infinity, so if I write GL, that just means GL infinity. This is the linear automorphisms of K infinity. Okay, so you should think of it as infinite by infinite matrices. Of course, GL has this canonical action. The standard representation is this V. All right, so the definition that I wanted to say was a GL and S will be for me the symmetric algebra on V, which I identify with the infinite variable polynomial ring. And GL will act on this. This is just a coordinate change, okay? So so my definition is a GL equivariant, and this is supposed to be S module. Oh, R, because I used R before. Is an R module in the ordinary sense with an action of GL infinity. Such that two conditions hold. So one is some kind of compatibility between all the actions. So G of Rm is G of R, G of M for all R in R, M in M, G in GL. And I mean, this is just saying that the multiplication map R tensor M to M is GL equivariant. And the second thing is saying that is sort of restricting the class of modules that can occur, class of GL representations that can occur. So M is, I will write smooth representation of GL infinity. This is usually called a polynomial representation of GL infinity, but since we're working with polynomial rings, I'm just saying smooth. And this essentially means, if you in characteristic 0, this just means that M is isomorphic to direct sums of Schur functors applied to the standard representations. But in characteristic P, you have to take subquotients of Schur functors because they are no longer irreducible. But it's not a big deal. Like, all you're saying is that there is some class of representations that you're working with, and those are the classes that are coming from Schur functors. It's the smallest class that is that contains the standard representation and is closed under tensor powers and kernels and co-kernels. And if you give me such an R module, you get a sequence as well. The way, and you know, this GL, this contains a subgroup, what I will call GL infinity minus n. And this is supposed to be matrices that look like this. It's just there's an n by n box where there is something, but then the rest of it is the identity matrix. Okay. Oh no, the other way around. This is identity here, and this is actually something is going on here. So this is supposed to be like infinity minus n because it fixes the first n things. And what you can do is such a GL equivariant module gives you a chain of GLN equivariant Rn modules by just taking invariance with respect to that. So if you give me such a module M, you can take, what you can do is you can consider, you can define Mn to be things which are fixed by that subgroup. These are all elements in capital M which are fixed by this subgroup pointwise. And this will be a module over Rn. And it'll be a chain like that we saw before. So if you take S and do this, you get Sn. Sorry, R and do this, you get Rn. And there, so this kind of gives a nice dictionary between like chains and kind of this this infinite thing. And one other very nice thing about working with infinite variable polynomial rings is that somehow you get to do more things. You get to do things in the infinite level that somehow you cannot retrieve in the finite level. And I mean this, so let me just define something. So, and of course, this forms a category, like there is a category of GL equivariant R modules. So that you can define, so fix E in N. So I'm going to define a functor, gamma E, from mod R to mod R. And what I'm going to do is, this is going to sort of, this is going to take a module M, and then it is going to map it to all elements M in M, such that It's going to map it to the maximal submodule that is annihilated by powers of the p to the eth Frobenius power of the maximal ideal. Yes, this is the maximal ideal. Yes, this is, and this is, yeah, okay, I should write n. Thanks. So essentially, this is morally you're taking local cohomology. I mean, this is well, this is not this is the taking zeroth local cohomology with the respect to m to the p to the e. And then you can, of course, yeah, you can do everything now. You can do like all the derived functor stuff now. So this is a left exact functor. So you can take its right derived functors, which I will denote by like Ri gamma e. And the thing is, in classical like Noetherian commutative algebra, if I and G are radical, like have the same radical, then the local cohomology with respect to I, J, and its radical are all the same. But really, what you need is that I and J are copotent in the sense that I to the n is contained in J and J to the m is contained in I. Whereas in the infinite setting, all these things are not copotent. So observe the crucial reason why this works. This definition works is meaningful since m to the p to the e and m to the p to the d are not copotent if d is not equal to e. So the point is that if you, no matter what power of the max, say let's say m and the Frobenius power of m, in like finite degree, if you take n times p, np minus n plus 1 power, I think that will be contained in the p to the e power by like pigeonhole principle or whatever. Whereas whenever you take any power of the maximal ideal in the infinite setting, you have the monomial x1, x2, x3, x4, x5, x6. Where you take all, you can keep on adding variables, and this will not be contained in any Frobenius power. So these are not copotent. So the gamma e's are all different functors. Okay. And then you can also define another functor, which I'll just call gamma. So gamma from mod r to mod r. And again, mod r is this category of GL equivariant modules where you send it to m is mapped to this thing. It is all elements in m which are annihilated by some non-zero ideal. There exists a GL stable ideal. That is not equal to 0, such that I to the k, I to the r n is equal to 0. So somehow gamma is supposed to be like the limits of all the gamma e's. And again, this is left exact, and you can define the derived functors of this. The I can change according to the element. That is correct. So here is the main result. Yeah. Oh, maybe you need. Can't you do like I intersection J or something? Yeah. I haven't done that stuff in a while. I mean, I was just worried because the thing is, in this specific R example, the ideal lattice is very nice. It is, they're all, the GL stable ideal lattice. It's kind of, it just contains the Frobenius powers of the maximal ideals, products of them, sums of them, and so on. So I thought it was maybe like a particular thing to this, but I think in general it works. I think. You can take any GL stable ideal. So the Frobenius powers of the maximal ideals are examples. products of them are example, quotients of them are example. More generally, there is a, yeah, I mean, syzygies of these things, and yeah, I don't know. The category is sufficiently rich. I mean, at least in characteristic 0, this is equivalent to the category of what's called FI modules. I don't know if you've heard this. It's functors from FI, which is the category of finite sets with injections to K vector spaces. So it's and it's very important in like topology and stuff. So there's yeah, it's an yeah, the category of modules is fairly big. Like 12 minutes, right?
So,
I guess. Yeah. Oh no, I have 2 minutes. 2 to 12? Okay.
Yeah. We should leave some time for questions.
Okay. But I guess people have been asking questions.
Yeah, people have been asking questions.
Okay, the hard part is like erasing things, which I. Okay, so here is the main result. So theorem. Now I need to do. And this is, but so let M be a finitely generated GL equivariant R module. So again, whenever I say finitely generated, I again mean that you can take like orbits of this group. So finitely generated GL equivariant R modules are not finitely generated in the usual sense. Then for all E, the right derived functors are gamma E of M is also a finitely generated GL equivariant S module. And similarly, you also have the statement for R gamma of M is also a finitely generated. This is not true as stated. What I mean to say is that it's actually a complex, and it is actually a complex of finitely generated GL equivariant S modules. But ultimately, what this means is that you have vanishing of local cohomology. So given a module M, there sufficiently large local cohomology will vanish, but that number can where it starts vanishing can depend on capital M. It can be non-vanishing for large enough I, depending on your module, and where it is non-vanishing, it is finally generated, which again does not happen for Newtonian rings even. And the same is true for the other functor, the derived functor of that. But the way to connect this back to the syzygy stuff is the following. Let me state that as a result as well. So we again have a finally generated GL equivariant R module. The following two things are true. So one, the slopes occurring in beta of M all have slopes, sorry, the lines, the non-zero lines occurring in beta all have slopes of the form p to the e minus 1 with e allowed to vary. And the second part is that these R gamma E's are precisely the ones which capture that. So R gamma E's, their resolutions, you can resolve them, and they are complexes, but that's okay. You can still resolve them, and they will be of pure slopey, which means they will not have any other lines of slopey. Any other lines of slope p to the d where d is not equal to e, p to the d minus 1 where d is not equal to e. And eventually the slope p to the e minus 1 component of beta of M will agree with that of R gamma E. The second part, let me again be fairly. R gamma E of M has a pure slope t to the e minus 1 solution, which agrees with that of M eventually. I think I should stop here, but this essentially says that you can extract the slopey part by taking local cohomologies with respect to the Frobenius powers. And I hope that even for symmetric monomial ideals, so which are a bigger class, you can take local cohomology with respect to, like, if you want to get like slope 0, you probably have to take local cohomology with respect to the maximal ideal. Slope 1 will be with respect to x1 square, x2 square, and so on. And slope d will be x1 to the d plus 1, x2 to the d plus 1. But yeah, I think I'll stop here. Thanks. It's in the derived category. So this is the statement is that R gamma preserves the bounded derived category. And R gamma E, and then you can just take the left effect R gamma E M tensor that with K to get the resolution. Yeah, yeah.
Conjecture of Nago and company.
Yeah, but I think it's there is where you have there is a way to talk about like modules over S infinity equivalent modules. So the definition is very similar, where it has an action of S infinity, and then G of R times M is G of R times G of M, and then the type of representations you can have are what are called smooth representations of S infinity, and that is kind of, there's a structure theory that you kind of have to build there to. I mean, this result uses a lot of about the structure theory of GL equivalent S modules. It's not like you can get it from finite dimensional setting or whatnot. You have to kind of go there and actually like do commutative algebra there. So they are trying to do commutative algebra, Nagpal, Snowden, and you, Teresa. But it's much more difficult. I mean, it's somehow when you're working with GL stuff, there are far fewer ideals that you have to kind of deal with. So there are far fewer modules, whereas with S infinity, there are just so many more ideals that you have to deal with, and therefore modules. Sort of what do you even take local cohomology with respect to is not clear, because it's not clear. Yeah, so